Okay, hello everyone. So today is our first full lecture in State of Bias webinar series. So last time we talked about, how cool is Bayes, what you can do with Bayesian methods, and these are all the projects that were only possible with Bayesian methods. So today, the format is a little bit different. There will be like very little advertising of the coolness of Bayesian methods, but rather we will try to understand what it is all about and how to think in terms of Bayesian statistician in order to make your own models that work for your problem. And when you see some Bayesian analysis, to understand what is this term about, or why do they interpret this thing or that. So this will be about understanding and focusing on knowledge gained. As for questions, you are free to submit questions to Q&A, but I would mention that it is quite problematic to spot them immediately. So from time to time, I'll try to look at the notifications and answer the questions after the slide is explained. So let's start our journey. So I graduated in Moscow from economics faculty and have some significant experience in economics. So I know what is monetary theory quite a little bit, but I forgot some things. Then I went to get my master's degree to Caltech. For those who are not familiar, what is Caltech? It's like MIT, but in Moscow, a separate entity, but they aim to get the same quality. I also developed PyMC, the probabilistic programming language, and I was there for a very, very long time developing variational inference and neural methods. And I was in a research group doing some deep learning stuff with Bayesian methods also there, and went to industry and met PyMC labs. So I'm here to give you the webinar, and I work now with PyMC labs. So our goal as me and you to understand what is Bayesian, what are Bayesian applied methods about and how to make maximum use of them. And we will learn different topics, including linear regressions. And you might not even know what we will talk about, because linear regressions, I will explain you, are quite different from what you get used to. Also, we will touch Gaussian processes, time series with Gaussian processes, hierarchies, spatial hierarchies with Gaussian processes, and how to think Bayesian to understand what is going on under the hood. And about grading. Yes, the grading system to forget. We're not in the university, so no grading, no assignments. I will not grade any of your homeworks. There will be none. So you may stay relaxed. But if you really want some training, and if you believe that you need home assignments or corporate training, just contact me and we will figure out how to deal with it. But so far, we're not in the university, so you will sleep a lot. And yeah, Bayesian methods are literally everywhere. People use them in modeling economics at large scale, at country level, for real world applications. Like in central banks, they usually work with Bayesian DSG models. For those who are not familiar with DSG, it is a model that gets all the economic equations all together. And this is really huge, and there is usually little data and a lot of knowledge about what is going on. So this is a bright example from economics. You can find a lot of applications following the Google Scholar link. Of course, Bayesian methods are used in industry all over the place, from marketing to pharmacy or finance, chemistry, everything. So really advanced people use Bayesian methods to put their expertise in place and get data-driven decisions. You can also use Bayesian methods in your research. So there is a lot of papers you can find in Google Scholar. They were possible with PyMC and Bayesian methods. So you can put your domain knowledge about your research topic and apply Bayesian methods there to get significant improvement in how you interpret things and which decisions are made out of your scarce data or complicated interaction model. So there is a lot of things where you can put this knowledge: industry, academia, everywhere. But what is Bayesian formula? And Bayesian formula was usually taught in university, but it is little explained in like simple words, or how is it connected to real life. So it is really problematic to get this connection from formula to real problems. And we will focus exactly on this topic in this lecture. First of all, we will talk about prior distribution, the most controversial equation formula in this formula. So what is the prior distribution? How to think about it? And one bright example that really touches this problem is one, not really famous, but one very bright paper. Where do priors come from? So in this research paper, they focused on really digging into the problem and getting all the sources that were helpful to get the prior distribution. And they were in the research question: how does the cannabis control, how does cannabis influences the brain for young adolescents? Of course, we think that cannabis is destructive for brain, but to which extent should we ban this use for adolescents, or we shouldn't care much? And to figure out, we need to make a scientific experiment to get this answer. And this is terribly complicated. There is literally no research about that. And you get the problem, it is really important, and there is literally zero data. And what to do if you're a data scientist? Well, probably you would wave your hands and do nothing, or very little. But when you have Bayesian instrumentary, there are some ways to get the domain expertise into the model. And we will talk about which expertise did the authors of the the paper yet, and how did they do this? As for the background, they used a game that checked the brain activity. And this game was to memorize the pictures in a specific order. One picture, they are shuffled over time, and you need to get the right order of the pictures you memorized on the previous step. So the game will train your long-term, short-term spatial memory. And this is quite important aspect of your brain activity when it comes to quantifying the effect of drugs and drug addiction. So this is what people look at when they study the brain. This game is called, this game is measured with self-ordered pointing test. So, or in short, SOPT, S-opt. I will refer to this once in a while. But they had few participants to participate in the experiment, and they checked them twice, a couple of times, but 2 times a year for 2 years. So they got 4 observations. And when this all began, they asked if they figure out if the participant is addicted or not addicted to light drugs. And here comes the central part of this paper with few data points, which are like 10 or 30, so very little data points. And they need to get this working with the linear model, and the way they figure out the price was astonishing. It was amazing. And you can use their approach with your new data, with your new problem, because the way they do it is quite general. So prior is something that you know before seeing any data. And in their case, what did they see before? What do they know before any data? They know the range of this SOPT score that people can gain in this during playing the game. So you at least know the practical range of what you're going to measure. And this is important if you're going to measure some customer responses. You at least know something about your customer responses. So there is practical range to measure. But this is like quite standard. This is what first comes to the mind. What comes to what is really tricky and a surprising way to get domain expertise is reading other research papers. So imagine you don't know what is going on in the research field, but you still need to get some estimates on interaction between, let's say, GDP and inflation. So you go and read a lot of papers. And this is what the authors of the paper do. So they went and read a lot of papers. Some of them were useful, and they took this information and the interactions, the estimate of the interaction between the variable of interest and their measurements. And they got the practical range for interaction effect. If you're an economist, you can do the same approach to estimate the orders of effect size between GDP and inflation. as for that problem, they did it for cannabis usage and assault. But the approach is widely applicable. And my finding was this is like super underused and often missed from the analysis or the approach or research when it comes to thesis or something else. People forget to include prior research results into prior distribution. Of course, you don't only rely on estimates of other research papers. You can also include your expert knowledge or someone's expert knowledge by showing pictures or discussing the effect size with an expert. And if he says this makes sense, then of course, yeah, don't touch it, or we need to correct that, make it larger or smaller. So corrections from experts also count. And the specific use from the authors of the paper was to include unrelated papers that had some side diseases that come with cannabis use and soft scores. So this was like indirect relation from cannabis use, but they tried to include that in the research. Something easy to get implemented are constraints. So if you know something is positively related, just make it the distribution of the effect size positive. So on the scarce data, the researchers managed to estimate the interaction between cannabis use and its long-term effects for people who are not addicted to cannabis use and those who get the healthy life and don't use cannabis. Despite these plots may seem with very wide standard deviation bars, it would be even close to possible to get this relation estimated properly. So all the estimates from linear regression models would be non-significant. But we are not about checking if something is significant or not significant. We're here to check if there is a relation and what is the most probable outcome of the relation. If the outcome is positive or negative, or we're unsure about the sign. And despite something might be not significant, with little data, the real benefit is to answer if something is supposed to be positive. And if the relation is, and in our case, the bad thing, it is negative. So if the relation is with high probability negative, then we're about to place some constraints on cannabis use, of course. But at least we can check this. So the controversial thing about prior distribution is that they are subjective. Of course, we talk to experts. Experts are subjective, but well, nothing is totally objective, and any objective thing might be challenged with common sense. Not placing any assumption is also wrong. So we need to be subjective in many cases. And for those who may need to convince somebody about his priors, and this is really important in research papers, just document what you are doing to get to this specific prior, to this specific number or practical range of values for interaction or high density interval. If it is documented, then it can be presented to somebody else. So if you have any questions concerning prior distribution and which sources might be useful to get this prior from, so you can go to the QA, ask the question, and I'll try to answer it before we go forward to discuss it, to discuss likelihood. Okay, so likelihood. Mm-hmm. So there is a question. Reading the question, does prior matter that much when you leave a lot of data available, when you have a lot of data available? Well, yes and no. There is a practical use case when you have a lot of data available, but if there is slight multicollinearity between some explanatory variables in, let's say, linear regression. When it comes to estimate the effect size for each of the interactions, this estimate is correlated. So the more weight is put to one variable, the less put to other variable. So you may want to balance it somehow, fairly balanced. And if you know that one variable is more important than another one, you can put prior knowledge that, we will explain it in, we will go deeper in this when we will discuss linear regressions, but you may put the knowledge that one variable is more important than another one. And you will partially solve this multicollinearity problem. And also other problems that inherit the underdetermined property for when it comes to estimates, they benefit from prior knowledge. If something is not non-identifiable from the data, it should be specified with prior distribution. And this is quite frequent. Next question. What is the most common way to determine prior distributions in marketing applications, for example, in MMMs? Usually you have past data available, and you may also contact the vendor to get an experiment and estimate customer acquisition costs. You may have some range for this customer acquisition cost. You may also know that it is not getting to be wild, like thousands of dollars per customer. So you may at least know some reasonable range for this important parameter. And team of analysts may also estimate the market size for each of the platform. And that's how you can get the saturation number for channels. But getting accurate saturation numbers for channels is unrealistic. So you at least end up with getting estimates for orders of saturation numbers. So if it is 1 million platform, so orders is 1 million. If it is multi-million people platform, so orders are different. So that is what about saturation numbers. Other variables and effect sizes are mostly about domain expertise, about the seasonality and etc. So it's also possible. So these two questions, and we will go forward. Is it okay to start with weakly informative priors first and then move to informative priors? There are instruments to check that your weakly informative prior is bad. We will touch this topic. And in general, you check the prior predictive distribution, and you can figure out if the prior predictive makes sense or not. So if you're predicting black hole densities, then your weakly informative prior is bad, and you need something more informative. Now, there are instruments to check if your prior is at least not awful. In case of prior, next question. In case of if prior, we need to take exactly prior distribution, and one of them exactly. I don't really understand this question. I may answer a different question, but I'll try to address the issue. So when we choose a prior for parameter, we need to pick exactly some family of prior distributions. So it should be some normal distribution, or gamma distribution, or student t distribution. It should be something. And as for distributions, they share some properties, like it is positive valued, it is zero avoiding distribution, or zero imposing distribution. So these properties are important when you choose prior distribution. So you pick between families, and your criterion is which properties you expect from the distribution. And if you find one, then you are good to go. And usually it is possible to find those. Not in all cases, it is possible to find a very good parameterized distribution. And it is a practical problem to deal with it. Okay, let's go to the next topic, not to get super late. I'll answer questions about likelihood after we finish discussing likelihood. Okay? Yeah. When it comes to likelihood, you just remember what you've got from classical machine learning. You have the objective function. And this objective function, treat it as likelihood. You will not mistake that dramatically. You will be almost correct, because likelihood estimates how good is your fit to data, which you provide to the model. If the fit is bad, then your likelihood is low. It goes other way around. But sometimes priors are really important to get some additional peculiarities about your data and inherit explain those nuances in data by estimating them more granularly. For example, this A/B test, a real life A/B test example of when you sell nuts. And when you sell nuts, it's not always you have all the customers buying your product. A lot of customers don't buy a specific product, but buy other products. But you want to increase sales for this particular product because you may have a contract with maybe your provider, with your partner, and you want to improve his sales. And when it comes to the problem, there are two ways to increase his sales: increasing purchase probability and increasing order size per customer. So either customers buy more, or there are more customers to buy the product. And there are many ways to deal with each of the problems. And why we're talking about A/B test? A/B test is exactly the example when all you really have is the likelihood and some of the domain expertise that is easy to put into the model. But likelihood is central in A/B testing. As for t-test, it is problematic to implement t-test for such type of data. This is widely discussed in forums with domain experts. So this weakness comes from checking two hypotheses simultaneously, and these hypotheses are very related to each other. It's not like comparing one test or another one, different experiments, different runs. It is all one experiment which deals with two challenging hypotheses. To take them both in account, you need something more than just t-test. And if you're a statistician without Bayesian methods, it's a tough problem. But if you're a Bayesian methodologist, this is a simple model that includes those nuances in one model. And we just have non-normal likelihood. That's not super complicated. And let's figure out which likelihood should we have. Okay, not all customers buy our product. So they have a zero inflation, so-called term for taking zeros in account. It might be wait times in a queue, defects on production, many other things. And this is lack of some event, lack of measurement. And we need to encode it somehow, and because it is something important about our data. And usually, if you go to check which distributions can be zero-inflated, you might find zero-inflated negative binomial, zero-inflated Poisson, all these discrete distributions. So it is. You may think that zero inflation is only about a discrete nature, but no, literally any distribution can be made zero inflated and just represent this distribution as a mixture. And how you generate a sample? It goes two-step. You first figure out if you have an event or don't have an event. Then you sample the event distribution. So like we have Bernoulli, if I'm to buy nuts, or go away with a milk or something else. And then if we were to buy nuts, we sample which amount of product I want to buy, and we get our sample. It's either zero or something else. You may play around with probability density distributions. We're not in university to go into mathematics. We're programmers. So we need to know how to make this working with PyMC or something else. But to do that, we need to represent our likelihood as a mixture. And this mixture is twofold. It has the mixture probability P. We've just got aware what is it? Is my probability to buy a product. And then there are two parts. One is the constant part, that is just to pick zero. Another one is continuous distribution, the gamma distribution. Names of distributions may be different in different probabilistic programming languages. but the idea is the same. Just represent this zero-inflated distribution as a mixture with two components. One is always constant, another one is arbitrary positive value with some probability. This helps to deal with complicated likelihood in this example. So we make an order with some probability, then sample the amount of product we want to buy. So good likelihoods are all about to understand your data, explain why you have outliers, which amount of outliers you have, and so on and so forth. And likelihoods like student t-distribution can estimate how many outliers you have in your data. So which portion of samples are outliers, which are not just normally distributed. So just treat likelihood as an objective function. But in addition, this objective function explains something else about your data. If it's just normal distribution, then it's more about objective function. But when this objective function is student t-distribution, it not only estimates the goodness of fit, but also explains how many outliers you have. If it is zero-inflated distribution, it's not only about goodness of fit, but also to explain how many zeros you have. So you get additional knowledge from this likelihood structure. When you understand your data, you can come up with a good likelihood distribution that explains all nuances of your observation model. So dividing the generation part from observation part. Sometimes it is useful to explain nuances of observations. Okay, if you have any questions, and I also already see one, that it's from Chris. Oh, I see the question. Let's go back to slide 19. What are you referring with sample in this equation? Is it the prior for p parameter? Like this. This a tilde is the generation process. So priors are detached from this likelihood. Prior is somewhere above this notation or below. It depends on which notation you choose. So P will follow some prior distribution. It may be beta distribution or uniform distribution. And it's then passed to the likelihood as a parameter. And that's how this P appears in the example. So this compositional likelihood, this mixture distribution likelihood has three parameters, alpha, beta, and P, which all follow some prior distributions. And we're talking about likelihoods, and we focus about which parameter explains which part of the observational model. I hope I answered your question. Okay, other questions? Okay, if we don't have further questions about likelihood, let's go to the posterior. And posterior is your surprise in data. And it is really surprising data because how you think about your data is your prior distribution. When you see your data, you see the goodness of fit, and it challenges your prior beliefs. And what you get in the very end is the posterior distribution. And if your likelihood really, really challenges you in terms of what you thought about your data, your posterior distribution will shift dramatically from the prior beliefs. And on compared distributions plot, when you compare prior distribution and posterior distribution, you will see that if your prior was challenged enough with likelihood, or if it was not. So you start with something, or like if you imagine, this can be like you think about a lot of things in real life. And then you go read some internet resources, you read newspapers, you read books, and then you change the attitude towards some problems. And that is how your prior distributions turns to be the posterior distribution. And then it goes into cycle when your posterior distribution is again your prior distribution. You go read about the domain problem again, and then you interact with your world model, update your priors with posteriors, posteriors become priors, and this is endless. And in Bayesian modeling, there is only one iteration. You have your prior beliefs, you get your data, you get posterior estimates. That's how you update your prior expertise with data. But there are still methods to utilize the posterior in newer models. So it becomes the interactive experience with new data. And the MMM example, I touched it a little bit in the intro session, but here we go again. And we talk about marketing example because here, posterior distribution is something central in the whole model. And posterior distribution is important in this example because it helps you to make informed data-driven decisions. When you work with such type of models, you really want to estimate risks of any of the decisions, and you compare alternatives with rigor. And mean value or point estimate is never enough. You need to understand the range of all possible outcomes of your decision, such that your investment is successful. And posterior distribution is the one that helps you to tackle this problem and go into the Bayesian decision-making area, where you create a financial model, and then you plug the posterior into this financial model to estimate the financial outcome given the decision you make. And all the possible outcomes that you estimated with the Bayesian model. Without the posterior, this couldn't be even close to possible. So that's why posterior is the central part of models that deal with Bayesian decision making. So just a quick recap. Prior is something we know without getting to data, talking to experts, something that is deliverable with words, or in very least email messages. So something exchangeable, something interpretable. With priors, we build the model, and ideally, the whole model is self-explanatory. So we can explain every parameter with plain English. And if it is so, you can discuss every parameter with your domain expert. So that's how you create the ideal prior for any problem that is at least valuable to a couple of people. And we got questions. Could you please give a simple example how to calculate likelihood in simple words? I'll answer this question, but I'll open the door. Okay, I'm back. In practice, you don't calculate likelihood by hands, but you rather specify the Bayesian model with code, like it is done in PyMC examples report. And every machinery to calculate likelihood is done by the package. So we don't think about code, about how to implement specific likelihood, but rather think about them on the model level. You specify the relations, and then you call the pm.sample, and it samples the model quite quickly. So the probabilistic programming language abstracts you from this complexity in calculating likelihoods. Okay, next question. I just want to let Max know that all Easter eggs he dropped in the slides are spotted. Thank you. Is the parameter a feature? If not, is the parameter a feature? If not, can explain this modeling using typical machine learning language like features data? Yes, sure. Let me try to do that for you. If you have a linear regression, it could be random forest. You have your data. Those are features or data. So these terms are, you can exchange them quickly. And parameters is everything that is estimated with pm.fit, so the outcome of like escalon fit something. Everything that is estimated with this call is treated as a parameter. If you're estimating linear regression, you estimate weights of this linear regression. If it is a neural network, you estimate all the weights for this neural network. Those are parameters. And in Bayesian model, this is something on top of those parameters, and that is called prior. So everything below the model, like features and parameters, stay the same, but you can calculate the probability of a specific parameter of your model to appear. And this is your prior. And the posterior is the result of calling fit. So I hope I answered the question. If not, you can type this question again to clarify the issue. Okay. Another thing that I think important in the model is the structure itself. So you can't think about a domain specific problem or model without thinking about structure. In classical machine learning, it is wildly and wildly weird that you don't think about the structure of your model. You just call the XGBoost, fit, data, targets, and you forget about the structure of your model. And with Bayesian methods, that is not the case. You don't just call fit. In between, you had to specify the model step by step, specifying the relations, specifying likely priors for every parameter or every group of parameters. So human in the loop is unavoidable. So every model becomes customized for a problem. And that is not always bad. Sometimes it is very useful because nothing is very similar to in many domains. So every problem is unique. And especially problems where Bayesian methods are applicable, these problems are indeed very unique. They are not you can't have one model that explains everything. And if you have one, it is probably overcomplicated. And this famous plot about bias variance trade-off really shows that having a complicated model, leads to huge bias and variance in estimates. But I like to admit that when you use Bayesian methods, you can somewhat control this bias variance trade-off when you increase complexity of the model. Because the main reason why this variance increases in classical machine learning is because there is no control over the priors of the parameters you add to the model. So the more the parameters you add to the model in classical machine learning, the more freedom you provide to the algorithm to fit to your data. That's the real source of variance. And in classical machine learning, there is an ideal spot between how complicated is your model and how good it explains your data. With Bayesian methods, when you increase the complexity of your model, of course, it can lead to increased variance, but this variance would be not in estimates, it would be in predictions you make with model. And to control the variance of these predictions, you need to have informed priors. And informed priors are those that constrain your model enough so it doesn't misbehave. And the model might be arbitrarily complex. And the downside would be the runtime of sampler. If something is not possible to estimate with given data, you will end up with prior very close to posterior. So you get little information from data to move your prior beliefs. If you have million parameter linear regression, it will of course take forever to sample, but you will end up with a model where the posterior distribution is close to prior, if this prior is okay, given this prior belief that a lot of features are useless. So in Bayesian methods, you kind of avoid this bias variance trade-off, but still you have to increase the model complexity step by step. Otherwise, as I said, you make your runtime infinite, and it is not possible to debug your model. And one of the examples where this structure is important, growing the complexity step by step, is time series models, where you have trend component, seasonality component, explanatory variables component, and something else. So if you start simple with just trend model, then you gradually add seasonality, then you can control every step that increases the complexity of your model. And you can easily track the spot where something is challenging to determine, and you can debug why this is not possible to determine. In example, we could have easily add a day model to this seasonality, but since there is no data about on day basis, only months, we would end up with a posterior distribution for daily seasonality or weekly seasonality very close to prior distribution, since we have no evidence to estimate the seasonality on this granular level. But if we were to pull everything together immediately, there won't be such a conclusion, because we don't do one-to-one comparison between steps. Let's wrap up. And the real question is when we need Bayesian methods. Usually, it requires some extra skills on top of about classical machine learning. You need to go deeper beyond just relation X and Y. You need to know how this relation is structured to recreate it and get all the parameters that you can talk about. But if you need just the uncertainty in predictions, there are a lot of methods that provide this uncertainty in predictions. Go and check out conformal predictions. They are great to get a neural network and make this neural network output uncertain predictions. That is totally fine. But not all problems are about predictions. And that's when I call this fit-predict paradigm really fails to deal with the problem. What you would have there, if you use Bayesian methods, you can explain everything about the parameters, given you specified the parameters in the way that you can interpret. You can tell about the parameter estimates to a non-statistician, so he understands you, because confidence intervals, traditional confidence intervals, are tricky to explain and are often explained wrong. But if you explain intervals, Bayesian intervals, they're totally fine to explain as just practical range of parameters. And with Bayesian tooling, you can have a lot of control of your model. You can control all the interactions. You can control over which domain expertise you put into the model, which assumptions you really imply on the structure. And you can get your feedback with the posterior and then use this insight to build yet another step in the model to complicate it a little bit more. So there is a continuous feedback loop between the model and the model. What is the difference between credible intervals and confidence intervals? The question, what is the difference between credible intervals and confidence intervals? To answer this question, let's think about the analogy. When you play darts, you throw I don't know how to say it, things to targets. And when it hits the target, if you throw really a lot of times, there is a cloud of your estimates. If you're good at throwing darts, then your estimates are close to the real target. And this whole cloud is all possible scenarios you could imagine the outcome would be. So every throw is your trial. And this whole distribution of throws is your posterior distribution. It is what you think the target would be. And at the middle of the target doesn't really matter because there is no real, in Bayesian approach, there is no real target, but it could be explained in many ways. The effect size could be estimated, explained in many ways. Oh, that's bad analogy. Okay, let's try a bit different approach. If you think about distribution, you think about the possible outcomes of effect size. And this is what you estimate. So the effect size could be from -1 to 3. And everything in between is likely to be true. And these are all your hypotheses. In classical machine learning, in t-test, this credible interval represents the interval where the so-called true value may appear with some probability. It may not be there, but you still can't interpret this interval as most probable events or most probable outcomes. And when you're about to plug this interval into simulation tools to estimate the financial model or something else, this wouldn't be correct. to be honest, this question to be answered really mathematically correct is tough. But in short, it is a lot easier to interpret the interval that is Bayesian interval because you interpreted this as possible events rather than something mathematically abstract. What are the main challenges when using Bayesian approach when presenting this to business audience? How do we gain trust that the results we got are valid? A lot of business people are indeed not familiar with Bayesian approach and what is posterior distribution or prior distribution. And as for me, it is easier to explain this in terms of the benefits that you gain from using Bayesian approach for data-driven decision-making. First of all, with classical machine learning, when it comes to discussing with business people, classical machine learning is often not a solution to such type of problems. And if it is, it is better solved with data analysis team. And the focus is really on the problems that are not solved with classical fit predict paradigm. And when it comes there are a lot of hacks that people do to get at least some estimates. And the first benefit that comes from Bayesian approach is that you have a rigor thing that transforms your domain knowledge or discussions into distributions that you plug to the model and parameters. So this is the first benefit. You constrain the model to behave the way it should behave. And sometimes it is really important with small data applications. So constraining the model to be good, even without seeing any data, is often important. If you imagine the bidding algorithm without any data or small data, when it on its burn-in stage, in order to make it pessimistic and not overly optimistic, you need to constrain the model. And you can only do this with a Bayesian approach in the way that you understand how it's done. And so your model behaves as it should behave in low data scenario. So you control the behavior of your model. This is often critical in applications where human oversight is expensive. Another benefit that comes from Bayesian methods, and you don't even need to say that it is a Bayesian benefit. You just say that what you get as estimates, you can use as a simulation of possible scenarios. And you convince that those simulations are trustworthy by going back to the step one, where you control the model to behave as it should behave and not misbehave. When it is not misbehaved, added data would only improve the accuracy of your decision. It will not make them worse. And you can spot that something goes wrong, but by looking at prior versus posterior, and that you can spot that something is wrong with your prior beliefs. So controlling how the model behaves, you also control the way the model, how the model gets the results and what posterior distribution you end up with. And simulating with this posterior distribution is like checking your prior beliefs versus data and iterating over all possible scenarios that are supported by your data and your prior beliefs. And to be sure about your decision at this point, you have to be sure about your prior beliefs and the quality of your data. If you have both check marks green, then your decisions are trustworthy. Okay, I hope this challenging question is tackled. If not, please type it once more, clarifying. Do we have any slides left? Of course, you can use PyMC, and with PyMC you forget about mathematical complexity. I think it doesn't make sense to advertise how awesome is PyMC, because everyone there should understand awesomeness of open source software, and that anyone with sufficient expertise or programming skills can contribute and improve the software, and that is a continuous process. And every year PyMC is even better than before. Everyone should use it. The last slide is with references to papers that were mentioned in this talk. So any other questions are welcome. Okay, if no questions are left, then a quick intro into the next lecture. It will be in next 2 weeks. And in next 2 weeks, we will talk about hierarchical models. What is the hierarchy? What are the challenges when you have hierarchy in your model? How to build hierarchical priors? And yeah, the recordings, Chris will answer this question. So we will learn how to specify priors step by step, starting with a simple model and then iterating to hierarchical model. Chris, your turn.
Recordings will be posted to the PyMC Labs website, YouTube channel, rather. I dumped the link into the Q&A. All right. Thanks, everyone, for coming.
Cool.